So I put myself in the program to talk about a joint project with Jan Spies, which has been in the making for over 7 years at this point, but hopefully we'll submit it soon, which is about optimal pre-analysis plans, and kind of in the general spirit of I guess this workshop, in terms of thinking about science as kind of social process, in particular as a process that has conflict of interest, private information, and thinking through the implications of that.
The worst
and so more specifically what this project is about is pre-registration, pre-analysis plans, which, as I'm sure you're all familiar with, have become kind of a standard requirement by now for experimental research in economics, but also in other social sciences, and before that in clinical research. Right, so in clinical studies, my understanding is this started in the 1990s, and then kind of interesting in terms of history of science, right? We have adopted the idea of RCTs for medicine, some time delay, and then the same thing has happened a bit later for pre-registration, which has also been kind of imported from clinical research. And the standard rationale that's given for why we should have pre-registration is that it guarantees validity of inference. So there's all these concerns about things like p-hacking, specification searching, publication bias. And all of those are like forms of selective reporting as a function of findings, which distorts inference, which makes like standard claims of size control invalid, which makes standard claims of unbiasedness invalid. And so the idea then would be that tying researchers' hands by deciding what you're going to report before you see any data, and somehow prevents them. And I mean, so for instance, Ted Begel and co-authors have been big advocates of this. There's also been some pushback from various people. There's been like, for instance, this 20 working paper by a number of editors from big empirical journals who argue maybe this has gone too far. Somehow it's preventing us from reporting discoveries that we didn't think of beforehand, and so on. What's kind of curious in all of this, and this has kind of been a pretty heated methodological debate in econ and in other disciplines, is that methodologists are almost completely absent from that debate. And in particular, if you open like a standard statistics textbook, chances are you're not going to find anything about pre-registration or pre-analysis plans. And I think there's a reason for that. And so one main reason is that the standard foundation for statistics is decision theory. And in decision theory, for instance, like the form that we've seen this morning about when talking about statistical testing, there is no timing consistency, right? You have like a rational agent, some form of utility maximizer. The utility maximizer typically has no reason to like cheat the future self, unless there's some kind of behavioral motives in there, but it's not part of the standard statistics framework. And so if there's no time inconsistency in your preferences, then there's no reason to tie your hands. But there's no you're not going to cheat yourself by selectively reporting. However, once you start thinking about the fact that there's multiple agents, then it starts to make a lot more sense, right? If you have some kind of conflict of interest where one party maybe tries to get another party to do something, then time inconsistency can arise under certain conditions. And so then you can end up writing down models where things like pre-analysis plans can make sense. And so then there's kind of two questions we try to answer in this project. The first one is, why do you need a commitment device to begin with? Second, what's the optimal pre-analysis plan, kind of generic setting. And more specifically, what we try to do, and the thing I believe that's generally a fruitful approach, is to incorporate insights from mechanism design into statistical theory. And by mechanism design, as opposed to kind of micro theory more generally, well, in a way, it allows you to stay very close to decision theory, to classical statistics. But one way to think about mechanism design is really decision theory is an additional constraint of implementability, right? So what you end up doing if you do mechanism design is you do decision theory, but subject to constraints that you wouldn't have in the standard stats context. And so in particular, you can kind of carry over all the standard theory that you have for statistics, but to constrained optimization rather than unconstrained optimization. And in particular, what emerges when you do that, as I'm going to show, is that pre-analysis plans actually are generically necessary for implementation. And I'm going to be more specific what I mean by pre-analysis plans. But we are just allowing for the possibility of sending a message before you see the data, where we leave the message unrestricted beforehand. But it turns out one way to implement the optimal thing is actually have the message be of the form of saying I'm going to use these decision rules, these statistical tests, these estimators. And what pre-analysis plans in particular allow you to do in such a framework is that you can leverage researcher expertise while maintaining incentive compatibility of non-selective reporting. Otherwise, without a pre-analysis message, you cannot get both of those. Right? You can have incentive compatibility of non-selective reporting, essentially by the receiving party completely dictating what statistical analysis you do. Right? So think the Food and Drug Administration just saying, this is how you have to analyze a clinical trial. But when you do that, then there is no more expertise on the, say, pharma company side that you could use, because exposed like any leeway there could be used for selective reporting to distort decisions. And so what's the model that we write down? We try to be fairly general. The model is kind of sequential. There is first a decision maker, so that's kind of the principle in the mechanism side problem. The decision maker commits to some decision rule. Then the analyst, before seeing the data, communicates some message. Ex ante, it could be any kind of message. Then the analyst observes the data and can selectively report things about the data. So here's kind of a key restriction. They cannot lie in the model. There's no scientific fraud by assumption here, but they can specification search, p-hack, and so on in order to get what they want. So they can hide things, but they cannot misreport things.
One reason that people object to pre-analysis plans is that they feel like upon step 3, when the analyst observes the data, that allows them to learn new things. They get new information. That means that sort of they wish they could change the pre-analysis plan. Do you allow for that in this model?
I mean, they can report ex post whatever they want, right? So this is not, when we say pre-analysis plan, we don't mean this restricts you to only report the things that you're going to report. This is just some message, and then you can report whatever you want today. However, so actually, when we started writing this paper, we wanted to write something about the costs and benefits of pre-analysis plans, kind of along the lines of these debates, trying to formalize them. We could not succeed at formalizing the costs in the sense of these exposed to regret arguments. I mean, like, kind of psychologically, it makes a lot of sense, right? You didn't think of something, and then you find, oh, but there is actually this cool phenomenon in the data. I would like to talk about that.
Just like a really concrete example is like maybe one variable you think is very noisy with a lot of missing data. So you say that you're not going to use that as an outcome. Then you get the data, and actually that variable looks like it's very high quality. So now you want to include it. And that seems.
That is actually something that's directly covered in our model.
Okay. Like that kind of learning after step 3. Like it feels like then.
And it turns out that
you shouldn't be punished in the same way. There was new information.
I would love to have this discussion at the end of the talk after we went through the model.
I think it's the technical stuff another way to think about this is to say that there is another agent other than the decision maker who's going to make the decision. So I'm thinking about an audience who then, if I see your pre-analysis plan, I'm only going to believe whatever you write in your pre-analysis plan, and so you're going to be penalized.
I mean, there's definitely multi-party models that you could write down. It's not that we're doing here, but we mentioned it's the 3-party model this morning. Could have such implications, although I don't immediately see how. But maybe we can again postpone this until afterwards. Because I would first like to walk you through like this logic. I think that's fairly generic here in this 2-party model. And then we can talk what model extensions or what's not covered here.
So this timeline seems very reasonable in an experimental study, but if it's like an observational study, sometimes you look at the data, at least get some signal about the data before you communicate a PAP, right?
Right, but then it's not a PRP, right? So, and what actually is gonna come out of the math here is that additional messages beyond the data here are useless.
Okay.
basic type of conflict of interest I'm gonna write down. Yeah, so a kind of a post-analysis message. There's no information content that can be delivered that way. All right. So slightly more formally, here's the model. There are two parties. There's the decision maker and the analyst. And so there's different interpretations you can have of those. So maybe the clearest one would be like the drug administration of the pharma company. But you could think about the reader of a research paper and the researcher. You could think about the journal editor and the researcher. Right? In each case, there's the researcher or analyst kind of is the one who sees the data and then decides what to report about the data. And then a decision is made, whether it's like approving the drug or publishing the paper or rejecting the null hypothesis and so on. You're going to have a generic message M, which we call pre-analysis plan, but again, you shouldn't necessarily think of this as the direct commitment to a particular analysis rule or whatever, it's just some message. Then we have the data. The data here we write in the form of this vector x1 through xn, which has some distribution p theta. The theta here is the state of the world. Can be of any dimension, live in any space, doesn't really matter for our purposes as of now. The same is actually true for the components of X. So what you should think of here is that this is kind of a stylized description of data, where really the different X's are different estimates or different hypothesis test outcomes and so on. So these are things that you could calculate and then you can decide whether or not to run them. Right? Typically, when you write an empirical paper, presumably you better run a whole bunch of regressions or a whole bunch of tests and so on. You're not going to put all of them in the paper. So these are the things we potentially put in the paper, but you might or might not. And so corresponding to that, we would have three index sets. There's the set K of all things we potentially observe. So this could in principle be infinite. Just to keep things technically simple, it's going to be finite, but it doesn't really matter. Then there's a subset of those, which is what the researcher actually observes. Right? So this is all the regressions you ran, all the tests you ran, and so on. All the data you collected in the experiment. And then there is a potential subset of that, which is what you actually run. And so this subset here, that's kind of very p-hacking or specification searching can come in, where you can decide not to report everything, and you might actually generically not report everything. And the researcher, of course, knows J when they make the decision, they know what they have. The decision maker doesn't, and that's what gives the researcher plausible deniability, that they can say, oh, I didn't actually see certain estimates, didn't collect certain data, that really is like
Say a bit more about J. I mean, you said it's sort of what regressions you did, but doing the regressions is a choice. Presumably this is sort of random, J.
Yeah, so I mean, there's some things that are outside of your control, some things that are not. Right, so I mean, it might be which experimental sites that you have, right? Example, I don't know which implementation part you could possibly find and run experiments with, or which subpopulations you collect data on, or how to compare this for survey data on. And so I mean, yes, there's choices on multiple stages here, right? Running the experiment, collecting the survey data, running the regression. So that's kind of all subsumed here. I'm going to, for the most part here, take the J as exogenous. Right, so the decision here is what to report about this event. So I mean, there's one version that you can think about this as a stopping rule, where they keep running regressions until they find something significant, and then they write it up. That's, I think, nice and perfect to this. If running the regressions is essentially costless. So
The decision maker or views on the J.
Absolutely. But I mean, the decision maker, what they do at the end is they implement the decision, which I'm going to assume is really valued. See the testing decision, publication decision, drug approval decision, a forecast, a point estimate. Right, so when you think about classical statistics, it's really about coming up mappings from these axes to infinity. So the test function is, that's what an estimator is, and so on. And what we're going to go for here is to ask which of these mappings can we actually implement in setting this There's the possibility of selective reporting. So here's the timeline corresponding to this model. It's just restating what happened in the previous slide. But we have the decision made by the analyst. The first thing that happens is the decision maker maybe picks a message space and commits to a decision function. Then the analyst observes whatever private information they have, right? So this is all the source of expertise. Could be expertise about what, I don't know, which things actually do have an effect, what subpopulations do have an effect, and so on. Could be expertise about which data you can actually collect, what experimental sites are available. So it's expertise in particular about both J and theta and interpretation, right? Both about what data are potentially available and what the true state of the world is, which drug is effective or not, or safe or not, and so on. And so they can condition their message on this private information pi. Yeah, so like simplicity here is the start out as a common prior, and then the version so comes from this private expertise here. Then you observe the data and decide which subset of the data or subset of estimate, subset of tests to report. And then it's communicated to the decision maker who then implements the decision function, which can condition on the message, can condition on which statistics were reported, and can condition on the value of these statistics. Right, so again, to emphasize, this is a model where analysts can withhold information, but they cannot lie. So I guess in theory parlance, it would be a model of partial verifiability. And so it's different from the canonical mechanism design problem where you can just pretend to be any type. Here you cannot pretend to be a type that has like received different data. Yeah, the components of access I already said, you can think of different estimates or different hypothesis tests and so on, outcome variables. And three leading examples here would be drug approval, hypothesis testing, publication decisions. You can come up with others. Before I go into details in analyzing that model, I want to spend some time walking through a specific example, right? So this is more special than our general model. But I think it ties more closely to the more practical intuitions of what could be happening in hypothesis testing. And later in the talk, I will return to this example, general theoretical framework. And so in particular, in this example, there are like two components, say, think two experimental sites or two subpopulations. Let's say you run a tested drug in this men and women. And there's a treatment effect, that's just for simplicity, I'm assuming the treatment effect is the same for both subpopulations data. And so for both of them, you get like an estimate that's normally distributed in this data. Right, so that's the outcome of two experiments. The analyst knows J, the decision maker does not. Right, that's what gives you plausible deniability. Because otherwise you can say, if I know what J is as the decision maker, I can always say you have to report all of J, or otherwise you're not going to get your decision that you want. And the null hypothesis that we want to test here is that theta is negative. And the analyst can selectively report. The goal of the analyst here is that we want to reject it. And going to assume later the decision maker here cares about having a valid statistical test where subject to size control they want to find. Yeah.
The decision
Kappa?
superset J.
Oh yeah. So this is all the things that's possibly available.
But I'm thinking to setting where kappa is basically its infinite size.
That's fine.
Okay.
Yeah. I think this is more of like a modeling technicality that we write this down explicitly. And I think in a way the infinite size makes it more plausible what we're doing in terms of I don't know what you could possibly observe, right? I mean, there's so many possible things we could look at, but I think that's really where as a decision maker my uncertainty comes to all about what it is to look at.
It seems like it's somewhat constraining that the all X's come from the same distribution.
in this example.
Right, oh, so
This is just like a simple example for illustrating things. It's not an assumption for the model that I'm going to analyze generality. But yeah, here it assumes that both of them are an estimate of the same theta. And so what I want to do now is walk you through 5 testing rules in this very simple setting. The first one is kind of the infeasible testing rule that you could only run if you always observe all the components. Then the naive test, which you could think of as a status quo that doesn't account for any p-hacking, which just takes whatever is reported as kind of full set and applies the critical value based on that. So this is kind of the test that allows p-hacking with the analyst, essentially. Then you can do the conservative multiple testing correction, which we heard a little bit about, and more about tomorrow, where we just make the worst case assumption about everything that's unreported. So this one is going to give you size control for sure, but possibly at the price of low power. Then you can talk about the optimal test without a pre-analysis plan, right? So this is kind of the one where we essentially cannot leverage any expertise of the researcher, of the analyst, but this is kind of like the FDA deciding this is how you're going to analyze the data. And the last one is the optimal test that can be implemented if you allow for a message before seeing the data. Right, so it has to be verifiably timestamped that it's before you saw the data, otherwise it's useless. All right, so let's go through these. What's the optimal full data test? We already saw the Neyman-Pearson lemma today. Neyman-Pearson lemma tells us the optimal full data test, you just take the significant statistic here, which is x1 plus x2, and you divide by root 2 to get the t-statistic, and then you compare it to the standard critical value of distribution, say 1.96 for the, or 1.64 for the one-sided 5% test, right? So rejection probability here is a function of x1 and x2, where we're averaging over j. This we're gonna reject in the top right. It's a function of the axis.
Thanks, Mike. Am I thinking about this right? So I can imagine the 2 things that you might observe, which is k. And you might observe j equals k.
Yeah.
I'm thinking that happens with probability of quarter. You know, with probability of quarter, you just observe the first thing.
Yeah.
With probability of quarter, you observe the second thing. With probability of quarter, you observe the nothing.
Possibility, yeah. So I mean, that's like the probability here would be the prior of the decision maker. Right. So I mean, at least a simple example, not
Yeah. So the if everything was reported that got received, the optimal decision rule would be, if you saw both things, then you would do this. If you saw what, but there'd be no.
Yeah, conditional on the j and then
selective reporting at that point.
Exactly. And as it turned out, that will actually be the solution, the optimal solution is that we use that here. We can implement that one in this example, but not without the pre-analysis plan. But let me walk through them in turn. Right, so this is kind of a textbook thing, there's no selective reporting. You observe the full j, you do your t-test based on the data, which in this case is just summing the 2 observation statistic. Then here, which you could call like the naive status quo, right, where the analyst picks whichever subset of components I report. And then for those, we just decide basically to apply like the standard testing rule, assuming those are the data that were available. Right, so that's like the decision rule, which applies a cutoff of c times 0 number of components reported. For the sum of the reported components. Right, that's just applying again the standard t-test for the reported components. What's the analyst's best response to such a decision function? Well, it's to p-hack. It's to select a subset of components that maximize their rejection if the goal is failure rejection. Right, and so this is exactly the specification searching or p-hacking. which people are worried about, that this causes distortions of size control here. And we can plot the probability of rejection, so this is particular probability distribution of availability, as a function of x1 and x2. Right? And so if x1 is large, I can just report x1, x2 is large, I can just report x2, sum is large, I can report the sum. So that gives me this little triangle here. And so I get rejection for any combination of those. And overall, I get a rejection probability that's possibly much larger than 5%. Right, so that's the naive test that doesn't take into account that we might have selective reporting, where it's not incentive compatible to just report I equal j. Being aware of that, you might want to do multiple hypothesis testing correction. Right, so that's one response in the literature, and that we're going to hear more about tomorrow. And one way to think about that is to say, well, there's this full set K that we could possibly observe. I'm going to do a correction for this full set, and anything you don't report, I'm going to make worst case assumptions about. Since for the full set here, we have the testing rule that rejects if the sum is bigger than 0 to C. If you don't report something, I'm not going to reject, because the worst case is always going to make the t set small, minus infinity. So this solution works in the sense that it controls size. It solves the size control problem. But the issue is it might have low power, possibly very low power, if the probability of observing all of the cases of the but in the limit of a case like this infinite set, then it's essentially 0. You have to correct for everything you could possibly observe. But it's incentive compatible and it controls size. Now, what's the optimal thing to do without a pre-analysis plan? But this depends a little bit on the priors of the decision maker. And here, what I'm assuming, it's a prior that puts a higher probability on x1 being available, x2 being available. Right, so experimental site 1 is more likely to actually successfully implement an experiment. What can we do? Well, what's the optimal thing to do? We want to have size control. We want to have incentive compatibility, meaning there's no incentive to somehow distortively selectively report. And we want to maximize expected power. And now I'm kind of restricting myself to not have a pre-analysis message. Then the best thing to do is, again, to take a full data test that make worst case assumptions about unreported components. So this is not an obvious thing, like this is something you're showing. And then choose the full data test that maximizes the expected power for this procedure. And if the probability of observing 1 is larger than 2, the solution might look like this, where you just do a t-test based only on the first component. And then implement that, and if you don't report the first component. So this yields again a test that has that controls size, and it possibly has much larger power than the conservative solution in the previous slide. And now the optimal test with a PEP, where we allow for a message before seeing the data. One possible solution for that setting that delivers the optimal, again, not an obvious claim, is that the analyst pick an arbitrary full data test that the analyst chooses, and again, make worst case assumptions about unreported components. And so this is kind of then a pre-analysis plan in a more literal sense, where the pre-analysis plan actually specifies a decision rule. And assuming that the analyst knows J when choosing the full data test, we are actually just going to, this is kind of equivalent to asking them to report this at J and corresponding to the test. And this delivers the testing procedure with the highest power subject to size control and subject to incentive compatibility. So here's kind of, again, summarizing the rejection probabilities as a function of x. Or alternatively, we can plot this as a function of theta, which is the power curve, which is not very visible in this picture for 2 components, but it can be the same logic for 10 components. Right, so x is like 10 elements. And then it becomes very visible what's happening. Right, so we started with the infeasible optimal full data test. It was this like dark line here. That's kind of the benchmark of as good as it can get, right? This is when you have no availability issues, no selective reporting issues. But we can't do that because then we can have kind of the naive status quo where we allow for p-hacking. And that's, of course, the standard concern that you get these massive size distortions from selective reporting. And so this example, like under the null, which is everything to the left of 0, you get rejection probabilities that go up to 50%, even though it's not 5%. But you get massive size distortions. Then we had the solution of the conservative test that one controls size. In this example, let's keep this power. This is always below 5%. Essentially, because the probability of observing all 10 components in this example is not very high. And so this is not really a solution either, because even with size, it doesn't have any useful power. Then we had the optimal test without a pre-analysis plan. That's a sensitive solution. It would be optimal if there's no private expertise on the analyst side. Again, it was size control and has kind of a sensible power curve here. But not one, not one. And then you see the yellow curve, that's the optimal thing you can achieve with a pre-analysis plan. Right, and so this kind of intuitively shows how a pre-analysis plan allows you to combine size control, incentive compatibility, but maximize power subject to that in a way that you could not do without a pre-analysis message.
What is the pre-analysis plan doing? Is it committing you to J?
No, it's actually generic, it's just a message. You can choose whatever message you send. It turns out that in the optimal solution for this one, it's equivalent to J, or it's also equivalent to communicating test.
So like in this example, then the decision maker only needs to compute worst case scenarios for sort of sub for the things that are in J but not I, rather than computing it.
Exactly. So everything that's not in the report in the intermediate sets and equal J that you ignore, just not there. Everything that is in the set, if you don't report it, then make worst case assumptions, which turns out to just not rejected here.
So it's much better than the conservative test because you plug that worst case into far fewer.
Exactly. Yeah. And because this example is extreme because the analyst knows which components are available, they know which experiments they ran and so on, or they will run. And because of that, there's no uncertainty at all of the J for them, whereas the decision maker has no idea what the experiments might be running. All right, so this was kind of a motivating example, and now let me kind of go to the more general theory. We are forget again about hypothesis testing, right? So I'm going to get back to that in the end, but this is just for a generic decision problem. We are introducing some notation. We already introduced a decision function, but I'm also introducing a reduced form decision function, which is a mapping from pi, the private signal, and the full data, the fully observed data as J of J. Right, so this is everything the analyst knows. So if the decision maker and the analyst are the same person, they would just repeat this function. Right, and this is also what kind of standard statistical decision theory in a way is concerned with, is finding the optimal R here. Right, so which could be, for instance, the optimal statistical test. But then we say such a reduced form decision function is implementable if there is an actual decision function A, which is a function of the message, the reported components, and the value of these reported components, such that the reduced form decision function is equal to this decision function for the best responses star, I star. All right, so this is just the textbook definition of implementability in a mechanism or a contract theory problem just applied to this setting. So, but the key thing is we have the reduced form decision function, which depends on everything the analyst knows, and the decision function, which depends only on what the decision maker knows. And say it's implementable if the reduced form is equal to A for the best response of star, I star to this function. Make sense? So this is kind of important for the rest of the talk. And then we have one assumption, which I think is the strongest assumption in the paper, but kind of gives a lot of leverage in terms of more concrete results, which is that the analyst basically wants a large game. Right, so the analyst wants to reject, they want the drug approved, they want to get published. So we are restricting the analyst preferences. And that is going to have a lot of implications for the set of implementable functions.
So are you using Bayesian Bayesian IC there, or like dominant strategies, or what are you using? Dominant
So far, I'm not using anything. I haven't told you at all what the decision maker wants, and I won't for a while, because I want to separate what's implementable and then what's optimally implementable.
Yep.
Right, so for implementable, I don't care what the decision maker objective is. What I do assume is that the analyst is an expected utility maximized participation. There's no dominant strategy thing because there is only one analyst, right? It's not a mechanism where there's multiple agents here.
Right, but it could be an optimal message X and I for each type, right? Or it could be on the each type Y. And or it could be the expectation present.
But M star is a function of pi, right? So the analyst chooses M star after observing pi.
Okay.
But before observing X.
Right, okay,
That's
so
fine.
after, yeah, okay, so it's
They actually choose I star after observing X and pi.
right, so it's not expected.
Right, but that's good. That's the key distinction here is the message chosen before the C, X, or after. That's what makes it a pre-analysis message, as opposed to something that ends up being useless. So here's the, I guess it's the more formal answer. The best response here is I star. That was actually simple for the chosen preferences because they just choose the subset that's maximizing A. If you want a large decision. That's kind of the p-hacking part, the specification searching part. And then kind of the first stage of the game, which was M star, here kind of the function P matters potentially. They maximize the expected utility conditional on pi. Okay. So let me give you, before I state the results a bit more formally, let me give you a brief preview, which is without pre-analysis plans, the implementable decision functions here are exactly the ones that are monotonic in J, monotonic in the sense of set inclusion. So reporting less can never make you better off. Right? And the decision functions which do not depend on pi at all. Right? So researcher expertise cannot be used at all if you don't have a pre-analysis plan in this model. If we allow for pre-analysis messages, then we only need monotonicity in J conditional on the analyst signal. So we get a much larger set of decision functions potentially that we can choose from. And again, conceptually what's happening is we can leverage researcher expertise. For instance, if they have knowledge about which J are available, we can use that in picking the decision function. Or if they have knowledge about which hypothesis are true or wrong, we can use that. Right, so there's a lot of improvement in performance you can get by using that information. There's the notion of implementability and there's the notion of implementation. But implementability is a function of A bar, but a given A bar can be implemented in different ways with different A's. But there's kind of two canonical ways of implementing them. The first one is kind of more the micro-theory textbook version, which is kind of a variant of the revelation principle where you just truthfully reveal pi, which is kind of conceptually nice, right? That's kind of what your textbook mechanism design revelation principle would say. Doesn't seem very practical because it requires the analyst to literally write down everything they know, which is a really hard task. But there's presumably a lot of things to know. And then the second implementation here, which is an alternative, is much simpler, and I think the realistic one, which is essentially a form of aligned delegation, right? So the way this works is that the decision maker restricts the set of possible decision functions, and then tells the analyst pick one of those, write it in your pre-analysis plan, and then that's the one we're going to implement after the fact. And that's pretty much what a pre-analysis plan in practice is, right? For instance, you say, pick a testing rule that's controls size, your choice which one, But whichever one you pick beforehand, we're going to implement after the fact. Turns out that's a way of the next one may be more technical. I won't spend too much time on today, but the set of implementable decision functions ends up being convex polytope, which means in particular if the decision maker is a Bayesian or expected utility maximizer, the objective is going to be linear, and so then the problem of optimal implementability becomes a linear programming problem over a convex polytope. And the solution has to be an extremal point of this, which is nice for theoretical reasons, but yeah, just say about that. So let me now state some of these results a bit more formally. So the first result here was, suppose no pre-analysis message is allowed, no pre-analysis plan, then the decision function is implementable if and only if it doesn't depend on pi at all. And it's monotonic in the sense of set inclusion. So if you have a set I subset of j, then a bar of x and I is or equal to a bar of xjj for any value of x. To be precise, almost any value. Right, so that's pretty simple. And the argument, the proof for that, this is the one proof I'm actually going to give you in full. It's actually pretty straightforward. One direction is, suppose this condition holds, we're just set a decision function equal to a bar, and then Gaussian monotonicity is never going to improve analyst utility to report less, and so therefore it's always incentive compatible to report everything, and then A is equal to a bar, and we're done. So a bar is implementable. On the other hand, pick any decision function A, and consider the best response I, well, it's maximizing A over choices of I, but the maximum is increasing the maximum over a larger set of possible index sets, so it's going to be an increasing function of J is of R. Right, so you use both directions really directly, and you get that you're implementable if and only if you have this monotonicity in terms of reporting more, no matter what the realization of X is. Just kind of as a side, right? Realization principle doesn't directly apply here because it's much verifiability. But in the standard textbook revelation principle, you can pretend to be any other type costlessly. Here you can't because you can only hide things, but you cannot lie. Here's the corresponding result now with a pre-analysis message. And the condition here then is that two conditions are necessary for implementability. One is the monotonicity, but now actually conditional on pi rather than unconditionally. And then the first stage, kind of the reporting of pi itself, that looks like the standard revelation principle where misreporting the type, basically. Any questions? So this is the complete characterization of everything that's implementable. And then the question is, how do we implement it? And I already mentioned kind of two canonical ways of doing that. One is directly reporting the type, right? So freelance plan is just you committing to paper everything you know, which you're not going to do in practice, because that's a lot. And the other alternative, which is kind of the more realistic one, which is kind of the delegation, where the idea is decision maker picks a set strict B of decision functions and tells the analyst to pick one of the decision functions in the set, and that's the one that's going to get implemented after. And it turns out anything that can be implemented this way. All right, so those were kind of the high-level results, but none of this is specific to hypothesis testing. All of this is just saying any decision problem where the analyst cares about a higher outcome, and you can selectively report. This is how you can implement the optimum. And so now the remainder of the talk is specializing the setting to the case of hypothesis testing, which leaves everything about implementability and about the analyst the same. But we're adding on top of that the decision maker cares about testing in the sense of maintaining size control and maximizing power subject to size control. Right, so in this generalized setting now, what we have is a null hypothesis. So this, I guess, ties in now nicely with what David was talking about earlier. If some null hypothesis fit or not. We think of the action here as being a rejection probability, but you could restrict yourself to the binary, but allowing for this complexification is a bit simpler. Because the ultimate outcome is binary, it's not loss of generality to assume that the analyst utility is just linear in the A. And size control is a little bit subtle how to define it here. Because, I mean, and that's true actually anytime you define size control, because there's obviously a question, what do you condition on, and what do you average over, right? So even with like kind of classical tests, you always have to ask, do you care about sampling, do you care about treatment assignment, some combination of the two, other statistics you want to condition on. So those obviously lead to different notions of what size control means. Here, the sensible one is conditioning on the index set, conditioning on the signal, and only averaging over the sample distribution of the axis. Right, so in principle, for instance, also allows size control averaging over the J's here, but that kind of leads to awkward conclusions. And I think it's not really the notion of size control you would typically have in mind. And then we have expected power, which is just the exact rejection probability averaged over the common prior and shared decision. Okay, and so this is the one that both care about, right? The analyst just cares about maximizing this. The decision maker cares about maximizing this, but subject to the size constraint. Okay. So now what are the optimal implementable statistical tests? Well, first what we have is the same that was true generally for implementability monotonicity, reporting more in order to increase the decision. But because of this monotonicity, what you get is that size control condition is also going to be monotonic in the index set. And so it's only going to be binding for the data. But so we only need to impose size control for the full data, and then we're done. Get size control for everything. And when we now look at the optimal test, which maximizes expected power, subject to size control, that's the first textbook problem thing. But then relative to the textbook, we have this additional constraint of implementability. And it turns out that the solution to this problem can be implemented as follows. Just ask the analyst to pick a full data test that controls size. Right, so that's a test that depends on xk for the full set of components k. Doesn't have to depend on all of them, but they can basically just let it depend on whatever they want. And then we make worst case assumptions about the unrecorded components, like in the example I started out with. And so this solves the problem from the principal perspective, decision maker perspective. And then this leaves the problem for the analyst how to respond to this mechanism. But what is the pre-analysis plan they should write in response to this? And it turns out the answer to that is in general a linear program that we can solve. So we wrote the app that you find on my website, which solves this linear program for you for some specific cases. And if you know J, it's actually going to be simpler, and it's going to look like some version of a likelihood ratio test. So here's the solution for the decision maker, or the FDA, if you want, kernel editor, which says that the test that maximizes expected power, subject to implementability and size control, can be implemented by requiring a pre-analysis plan which communicates a test that satisfies size control for the full data. So this is test Tx here. So under null, the probability that the expected value of T of x is to be less than alpha. And then the actual test we implement is just the minimum value of T of X over all x's that are consistent with the reported data. But so that's the part of making worst case assumptions about everything we don't report.
So you never worry about somebody reporting something that's not in the pre-analysis plan because the way that this model is set up, it would be never.
Exactly. So turns out in the solution to this model generically, you want to report everything. Right? So there's no reason for you to hide stuff, but because the incentives are set up in a way that hiding something never makes you better off.
I was just thinking there's some tests that you don't specify in the pre-analysis plan and then you run it. And I kind of can see in the way you set this up, there's just that would never be a rational thing to do because there's no pre-analysis plan, but I just feel like that's typically the direction if people can violate the pre-analysis plans, I would think. They report additional tests. They didn't.
Yeah, so I mean, that I guess raises the somewhat subtle question what the ultimate decision is here. Right, it's easier to think about drug approval or something like that, or think about like a fixed null, right? What steps you outside of this a bit, which maybe we want to talk more about later, is what if you add additional null hypotheses as a function of the data, right? Which is kind of outside of this here, like you have a fixed null and you're testing that. But you can't just say like, oh, my null is that the drug is not effective, and the alternative is that it is effective for some subgroup, and then I keep randomly adding subgroups. But that's kind of precluded by the solution. But you can't just like, or different endpoints, or
I thought it was really hard to determine a test that has full size, perfect size control if everything is not independent of each other. And you can't use, I don't know, whatever standard. So is it in practice, is it is the implementable thing actually implementable? Is it easy to determine that?
I mean, if you want to add additional constraints of the compatibility or something like that, but this is in any case like the classical textbook for a problem of statistics, right? You're gonna find hundreds of books that are gonna tell you how to do this for different cases. And what's kind of new is just this, let's say, just do this for the full, potentially available full data, and we make worst case assumptions about the rest.
What was the analyst complement J?
In this model, it's given to them.
Right, but then there are like some concerns like the one that David was posting in the morning, that if I believe that my treatment effect is very noisy, which is rather select a very small sample size in first place. Like I have like a prior on those treatment.
Yes, so that's not part of this model. I think that's an important concern. It's not covered here. Here, in a way, the margin is really just selective reporting. It's not endogenously deciding how many experiments to run, which I think is an interesting additional layer, which complicates things further. Just this. But yeah, so again, like under the model assumptions, this solves the problem for the decision maker. And then that raises the question, what's right, so let's just to briefly go through the argument again. We already saw for the generic case, right, that anything that can be implemented can be implemented by navigation in this model. We also saw that generically anything that's implemented is monotonic in the index set. And so if you have these two properties, then you get basically that you only need to impose size control for the full data because of monotonicity that implies size control for the sets that you might have. And furthermore, subject to size control and monotonicity, we have that analyst and decision maker are aligned. So all the remaining decisions, and sometimes you can delegate, because subject to that, they both want to maximize power anyway. Right, and so that's exactly how then the researcher expertise gets used here, is to decide which of these full data tests is going to give you highest power, because they know which hypotheses are interested, or which version of the hypothesis is interested in tests. They know which experimental sites are available, or which endpoints they can collect data on, and so on. So this kind of solves the problem for the decision maker, and then what we're left with is solving the problem for the analyst, how to best respond to this. And that generically looks like this. But so that's not a linear programming problem. They want to maximize, we call it interim expected power here, so expected power conditional on signal pi, but averaging over whatever the distribution for x and j is conditional on pi. But subject to the constraint of picking a decision function that has size control for the full data, it's bounded between 0 and 1. It's monotonic. Right, so that's a linear programming problem. If x is finite support, then you just plug it into your solver for a linear programming problem and you get a solution. You can furthermore characterize the solution because the constraint set here is a polytope. So we have that a solution at least has to be at an extremal point of the polytope. And maybe the most interesting and simple conclusion here is if the analyst actually knows J, when they specify the previous plan, which might be the case in that settings, or to know which experiments they're going to run, what data they're going to collect. In that case, the solution to this problem is pretty simple, which basically just looks like a likelihood ratio test. It's a version of the name Pearson lemma, except it's kind of a subtle twist here that it's a likelihood ratio of the marginal probability distribution of the data with the alternative, which is averaging over the interim posterior of this from condition of the expertise, but averaging over the remaining uncertainty of theta j. Right, but it's still like a ratio between this likelihood and the likelihood of that gives you the test that maximizes the expected power subject to size control. So maybe confusing, not that familiar, but it's a pretty simple solution that is pretty practical in many cases, I think. So that maybe gets a little bit back to your question about how easy is this to calculate. Not that hard, I would say. All right. Yes, let me conclude, and then we have to discuss further. So what we have in this model and more general models of this type is that if there's multiple agents, right, so as opposed to the standard statistics model of a single decision maker, and if there is conflicts of interest and private information between these agents, then generally we have not all decisions available. And then we can kind of draw on the framework of mechanism design, which I think is nice for the purpose, because it allows us to, in some sense, stay very close to classic statistics. But it's not just like saying, well, here's the solution of some kind of market equilibrium of science or something like that. No, it's still kind of in the prescriptive framework of statistics that says how you analyze data. But it allows us essentially to do classic statistics subject to an additional constraint of implementability. And particular framework that we look at in this paper is one of partial verifiability, where kind of the margin of action of the analyst is to selectively report things, so they hide information but reliable information. And what you then get in this setting is the pre-analysis plans, which have no role whatsoever in classic single-agent decision theory, which presumably is why they don't show up in any of the statistics textbook. Books suddenly become generically optimal part of the optimal mechanism to get the best implementable rule. And so what we then do is, I think, give a very full characterization of implementable rules generically in this framework and optimal implementable hypothesis tests. But of course, there are many considerations and possible mechanisms that are not part of this. As you already mentioned, the question of endogenously choosing J or endogenously choosing how many experiments to run. There's also other things that you might consider in a more dynamic setting. Reputation, which maybe we'll hear more about later, or like research credibility or something like that, adversarial refereeing, things like that are not part of this. But yeah.
Yes, it's another dynamic issue that may be related to what we're saying here is the actual revision of this of the plan in this framework. You think of an extension that, because in practice, often you allow revision. Can you say something about this? Need to have additional information. No. How would you extend the model to make sense of that? Or can you
I mean, so yeah, again, we started out wanting to include that in the model, right? And again, at least I couldn't come up with a coherent way of doing that. Because I mean, psychologically, again, this exposed regret makes sense to me, right? I see this thing in the data that I didn't think about before, and I regret that I cannot use it now. But from an ex-ante perspective, I couldn't come up with any way of making sense of that was kind of coherent to maximize any notion of ex-ante expected utility or something like that. I mean, it's also here, like, it's not like this, at least the type of solution we have here, right? It's not like it's preventing you from reporting anything. Here you report everything in the solution, right? So there's no sense in which there's like information that gets lost here. It's just you don't get to revise the decision rule exposed as a function of the data, which is kind of what this exposed regrets argument is going for.
I would go at that. We had the analyst basically as a type, which is something that's the cost of generating data.
Yeah.
And we could just have that, periods where you can gather one piece of data, you can gather X1, X, the multi-dimensional thing. You can gather the sample of one. You can do women and whatever, but you do it sequentially at a cost.
Yeah.
And you might learn that the optimal policy might be the next thing, just statistically, the next thing that you would do would depend on what you learned from the first thing.
Sure.
Now, what the mechanism design problem it would look like, what the decision maker would say is, you tell me what your type is, how much it costs to get the data, and then what I will tell you is to conduct the optimal decision rule, but subject to incentive compatibility. So it would sort of have a lot, it would be, a lot of it would be very like what you've got, but it would also allow some.
So if you can try to rephrase that, it would be like any sequential decision rule of the time you describe, or this optimal stopping or something like that, you can, because it's still a function of the full vector X, right? So you can always rewrite the extensive form as a normal form or something. But then the other part,
the person would be instructed, well, there'd be two ways of sort of, what a direct measurement is, you just give your type, but another way of reporting type would be to give a pre-analysis plan. What we're going to do is first we're going to sample, what the rate of this thing is in women, and then depending on what we observe there, we will go to children or men or whatever.
I think so. Again, like where I was going, like you can write that as a function of the full vector X, but I think what's missing from our model relative to that is that then you have like a cost function which depends on how you go down the tree or something like that. Right, so that's like changing the analyst utility function relative to our simple one, which is only about the ultimate decision that's being made, as opposed to like that's how you go down the path of the tree. Yeah. So it's in a way an extension of the utility function by incorporating the cost of collecting data or something like that.
Certainly would have the cost of data, but in some sense that's sort of natural in mechanism design, that there's something about the guys who are applying for this thing that you don't know about. In some sense, the lower dimensional that is
we have the pi here, right, which is completely general. That is like an analyst type and whatever information they have. but we don't have the cost of collecting data. Right, so I guess like another way of putting that would be that the analyst utility function doesn't depend only on the decision A, it also depends on the set I of reported statistics. Right, or maybe not the cost of reporting more I's or specific I's. But I still don't see how that would get you this exposed regret time.
No, there wouldn't be any regret.
Okay.
This would not be visibility and analysts. They would be responding.
Yeah, so that goes in next what the meter system working on, right?
It would be, you know, it'll be a-
So
not saying it's doable.
I think actually
But
I
then
think
you
it's
think
probably which would be in a way like a hybrid, I guess, between what the leaders doing this paper in the sense of take this model, but modify the analyst utility function to include I in some form. For instance, by penalizing the larger I. And then I don't know off the top of my head what the solution to the problem would be in that case. Because obviously you wouldn't generically want them to report all the J. It's costly. And it's the other thing that's not really in here, right? There's no participation constraints there. It's just costs.
Here, you can decide whether to run some subgroups analysis. And then if you get a good value for one subgroup, you can always set the driver of that particular subgroup.
Yeah.
This can use profits.
Right. So there's another generalization right here. The action space is by assumption one-dimensional.
Yeah.
Right. So I mean there is a way of so here I assume that V is monotonic in a one-dimensional A. All the implementability results, if you replace A by V, carry over the general multiple decisions and stuff like that. It's just that it has a lot less structure in a way when it's about V rather than A, right? So you can, but what you can have is that it's V of HR has to be monotonic, J, so so I think that's the way to formulate and generalize these results. It's just that, yeah, it's less clear how to interpret it in that case. And initially, we were thinking of having like a section here with like say multiple decisions or stuff like that. But then in a way, it's not obvious how to do that in a way where it's not becoming completely separable across these component decisions. But it's almost like you have a pre-analysis plan for men, you have a pre-analysis plan for women, and so on. You just have like separate approval decisions for all of those, which then kind of boils down to this again. I keep it long, but I mean, I would think of this as also start of an agenda, right? It's not that the final answer and all of this. I do like the model here that is fairly generic and some dimension of like selective reporting. And I do like how like very cleanly it pops out the pre-analysis plans are the optimal thing to do under certain conditions, but there's certainly a lot more to be done in space. And, all right. Let's leave it at that then.